Hello, everyone. Welcome to Stat 315, Recitation 3. Today we're going to be going over the empirical rule and percentiles. So the empirical rule is for approximately symmetric, mound-shaped, unimodal, bell-shaped data. And approximately 68% of the data are inside one standard deviation of the mean. 95% of the data are inside two standard deviations of the mean, and 99.7% of the data is inside three standard deviations of the mean. And we'll go over what that means in question one when we have to compute the number of measurements within 1, 2, and 3 standard deviations. And then we'll also be computing percentiles. And the pth percentile is a number such that p% of the data falls below it and 100 minus p% falls above it. So let's get started. So first, question one, we're given a sample of 25 different measurements. So here are 25, and there's two ways to do this, either by hand or using R. So I'll show you both ways. First, I'll show you how to compute the items that question one asks for by hand. So first we have to compute the mean. So the mean is also known as X bar. So you're going to add all of your X's and all of your data points and then divide it by the total number of data points. So here we know our total is 25, and we're going to add up 7 plus 6 plus 6 plus 11, so on and so forth. So it'll look like this. So I'm going to go through and add up all of them. So 7 plus 6 plus 6 plus 11 plus 8 plus 9 plus 11 plus 9 plus 10 plus 8 plus 7, so on and so forth. You get the picture. And then divide that by our total, so that's 25. So when you plug that into your calculator, you should get 206 over 25. When you add all of them together, you should get 226. And then we'll divide that by 25, and then our answer is 8.24. So our mean is 8.24. All right. So now we have to compute the standard deviation. So the standard deviation, how to compute that. So we're going to take each data point, subtract it from the mean, and we found that the mean is 8.24. And then we're going to square that, and we're going to add up all of those. So we'll do like the first data point minus the mean squared plus the second data point minus the mean squared, so on and so forth. And then we're going to divide that number by n minus 1, which our n is 25. So it would be divide that by 25 minus 1, and then we'll take the square root of that. So when you do it by hand, it should look like this. So we're just going to go down the line. So we'll take 7 minus 8.24, which is our mean. We're going to square it, and then we're going to go to the next data point, which is 6. So 6 minus 8.24 squared plus 6 minus 8.24 squared. And we're going to do that for all the different numbers. And then our last two numbers are 8 minus 8.24 and then 6 minus 8.24 squared. And then we're going to divide that by 24. So when you plug this into your calculator, the numerator should simplify to 80.56. And then we're going to divide that by 24 and take the square root. So we're taking the square root of 3.3566, repeating, and we'll get 1.83212. So what did I want to say about this? Oh, so for the standard deviation, notice, so people might wonder, okay, why are we subtracting? So here we're taking the deviation from the mean. So every data point, this is a way to remember what the standard deviation is. We're going to take the data point, subtract it from the mean. This gives us the deviation from the mean. And we're squaring them because some numbers before we square them will be negative, like in this, like 7 minus 8.24 will be negative. But here, well, we can also get positive deviations, 8.24. So when we square them, we just get like the magnitude of the deviations. And then we'll, yeah, and then you divide it by the sample size minus 1. All right. So if the thing that I was telling you guys about subtracting, getting what I just said about deviations and magnitude, you can forget that. I just want to give you some explanation. If it helps you, great. But as long as you know how to compute this, that's the main goal. And then I'll also show you how to do it in R. So I guess I'll hop over to R right now. So here we have the data. So I entered in the data. So we have 7, 6, 6, 11, all the way to, 8 and 6. So we have everything written here. And then we're going to have S1 be the sum of X. And then S2 be the sum of X squared. The length, we want to find the length of X to make sure, okay, we have all 25 points. And then we can compute the mean and the variance. This is how you would compute the variance here. So you would take S2 minus S1 squared divided by 25, and then divide that by 24. And then S equals the square root of the variance, and then that gives us the standard deviation. So if I want to run this code, we should get the same answers as before. 8.24 is our mean, and 1.832121 is our exact standard deviation. Okay, which matches what we got. All right, so I'll keep it on the R for one more second, just in case if you want to look at that code before I go to part B. All right, you can always pause too. Oh, and I did notice from my previous video, I wish there was a way to zoom in, but I don't think I can. It seemed a little blurry, but all right, so on to question B. So B, we're going to count the number of measurements within 1, 2, and 3 standard deviations. And remember here, our empirical rule, this will kind of give us an idea of how much of the data is inside 1 standard deviation, how much of the data is in 2 standard deviations, and so on and so forth. Okay, so first let's compute how many measurements are within 1 standard deviation. So we got our standard deviation, and I'm just going to round. So we have 1.83. That's what I'm going to use as my standard deviation. So to find the number of measurements within 1 standard deviation, we're going to take the mean, and we're going to add 1 standard deviation from the mean, and we're also going to take the mean and subtract 1 standard deviation from the mean. Then that will give us an interval, and then we'll count, okay, how many of our data points fall within this interval that it gives us. All right, so first let's just focus on this left-hand one, and I'll go through each one of these. But this is for computing the number of measurements within 1 standard deviation. So I'm going to take the mean, add it to the standard deviation, and then I'll also subtract 1 standard deviation from the mean, and we get this range. So we have 10.07 and 6.41. So now we want to count how many of our numbers lie, how many of our numbers are greater than 6.41 and less than 10.07. So if this were an interval, how many of our numbers fall in that interval? So our 6s will be out of the interval because we have 6. Our interval starts at like 6.41. That's our lower bound. So our first number in the interval is going to be 7, and we only have whole numbers. So we're going to look for the number count the number of 7s, 8s, 9s, and 10s. 11, notice 11 is outside that interval because 10.07 is our upper bound. All right, so what I did was I first went through and counted all of the 7s, then I counted all of the 8s, all of the 9s, then all of the 10s, and I added all those together to get the number of measurements. So if we count the number of 7s, that would be 1, and follow my mouse, 2, 3, 4, 5, 6, 7. And then I counted the number of 8s. So you just go through and you count the number of 8s. So there should be 3. So 1, 2, 3. And then I did the same with 9 and 10. So there were 4 9s and 4 10s. So when you add 7 plus 3 plus 4 plus 4, you get 18. So we have 18 measurements within one standard deviation. All right, so now let's compute how many measurements are within 2 standard deviations. So here we're going to take the mean, which is 8.24, and we're going to add it to 2 times the standard deviation. So that would be 2 standard deviations if we add 2 of them together, multiply 2 of them together. So 8.24 plus 2 times 1.83 is 11.9. That'll be our upper bound in the range we're looking for. And then we're also going to subtract 2 standard deviations, and our lower bound will be 4.58. So in this scenario, we'll be looking for the number of 5s, because 4 is outside the interval. So we'll start at 5. So 5, 6, 7s, 8s, 9s, 10s, and 11s, and then 12 will be outside the interval because we're going to stop at 11.9. All right, so if you count the number of 5s, you'll get 1. If you count the number of 6s, there should be 3 6s, and then 7 7s, 3 8s, 4 9s, 4 10s, and then 2 11s. So when you add that all together, you get 24. So we have 24 out of our 25 measurements that fall within 2 standard deviations. And then for counting the number of measurements within 3 standard deviations, we're going to do the same thing we did before, but instead we're going to multiply our standard deviation by 3. So we'll do 8.24 plus 3 times 1.83, and 8.24, which is our mean, minus 3 times our standard deviation, which is 1.83. So our upper bound in this scenario is 13.73, and our lower bound is 2.75. So here we want to count the numbers of 3, 4s, 5, 6, 7s, 8, 9s, all the way to 13. 14 would be outside that. So we want to count the number of these, which all of our data in this scenario falls within this range, because we don't have any 2s or lower, and we don't have any 14s or higher. So all of our data, if you go through and count, would be the number of measurements that fall within 3 standard deviations. So this would be 25, and that's cut off for some reason right here, but it's a 25. All right, so that completes question 1B. Now question C is we want to express each count as a percentage of the number of measurements. So here we have 3 different counts, and we want to express them as a percentage. So we're going to take each number and divide it by the total of measurements, which is 25. So we'll take 18 divided by 25. That'll give us 0.72. So the percent would be 72% because you multiply that decimal by 100. And then in this scenario, we had 24 of our measurements that fall within 2 standard deviations. So that would be 96%. And then in our third situation, where we're dealing with number of measurements within 3 standard deviations, we have all 25. So that's 100% of 100% of our data falls within 3 standard deviations. All right. So now part D is we're going to compare these percentages to the empirical rule, which is listed above. So right here. So try to keep in mind for 1 standard deviation, it's 68, 2 standard deviations is 95, and 3 is 99.7%. So when you fill this out, this is from that empirical rule, and then this is what we actually got. So for 1 standard deviation, it was 72%, then 96%, then 100%. So we're comparing, and they're pretty close. They're all pretty close to each other, especially 2 standard deviations is really close to each other. What we actually got versus the empirical rule. But the empirical rule is just, approximately that. So it could be different every time a little bit, but you should never get something that's like completely different, like only have your actual be like 30% of the data or something like that. You want it to be somewhat close to these numbers, which in our situation, they are. So that is good. All right, so now part 2A, in a statistics exam, student A scored 60th percentile while outperforming 150 students. So now we want to find out how many students total there are in the class. So whenever I'm asked questions about percentiles, I always draw a graph or a histogram, sorry. So, and it helps me out. So here we have this student, student A, and they're in the 60th percentile right here. And we're given that there are 150 students. Well, he outperformed 150 students. So here, 150 students, we always read them like left to right. So we know 150 students scored less than the 60th percentile student. And so we want to find out, okay, how many total students? So that would be X in this situation because I set it up like this. So we have 150 students equals 0.6 times the total. So we have our 60% times the total. And we're trying to find out what that total number of students is. So I'm just going to solve this algebraic equation. So the first step, I'm going to divide by 0.6 on each side here. And then you'll get that X equals 250. So 250 students, that's the total number of students in the class. All right. And if you notice, so just to go back up here, what this is saying, so the pth percentile, so in this situation, we were dealing with the 60th percentile. So let's say we're dealing with the 60th percentile just to make sense of this statement. So the 60th percentile is a number such that 60% of the data falls below it, and 100 minus 60, so that would be 40%, falls above it. So here we have 60% of the data that falls below it, and then 40% of the data that falls above it. And so that's why we multiplied 0.6 times the total, because below it is 60% of the data. So, and here the student outperformed, so performed better than these. All right, so let's go to the next one. So B. So another student, B, in the class scored 42nd percentile. How many students outperformed student B? So here are 42nd percentiles, let's say here. So we want to know, what is this red area? All right. So we know from previously that there's 250 students, because we just found that out. So we're going to want to hold on to that information. So there's 2 steps in solving this. So first, we're going to figure out what is this yellow area here. We want to know what percent of the students, or how many students are, scored below student B. So we're going to take 0.42 and multiply it by the total. That'll give us 105. So here there's 105 students. And now, but what we're interested in is the red area under the curve. So we're going to take the total, because under the curve, this whole area under the curve should be the total number of students. So if we know the total and we know this part, we can subtract the yellow from the total to find the red part. So, or the right-hand side. So 250 minus 105, which is the yellow part, will give us the red part on the right-hand side, which is 145 students. So 145 students outperformed student B. So 145 students did better than student B. All right, on to C. So student C scored points which were less than 40 students in the course. What was student's percentile rank? All right, so here, draw a graph again. It's really helpful. So it's good to have practice. When you're doing any type of percentile, I always encourage students to draw a histogram. Sorry, I keep saying graph, but pictures are worth, a million words, or whatever the saying is. Anyways, okay, so here we have, so student C scored points which were less than 40 students in the course. So here, if we were to draw the information we know, we would say, okay, so student C did pretty good if we know that there's a total of 250 students and only 40 students did better than student C. So I just ballparked, okay, student C would be somewhere here under the curve, and we're given this information. The blue area is 40 students. And we want to know, what is this percentile rank? So there's a few steps to this. So the first step, we need to figure out, okay, how many students are in this green area? And we know that our total is 250. So we're going to take 250 and subtract 40. We're going to subtract this right-hand side of C to get 210. So here the green area is 210, the blue area is 40. And now, because we work from left to right to compute the percentiles, we're going to do 210 because we need this area, the area to the left of C. So we're going to take 210 and divide that by the total 250, and we'll get 0.84. So student C scored in the 84th percentile, which is what we would expect, because like I said before, student C, must have done pretty well if only 40 students out of 250 scored better than him. So 84th percentile. All right. Question 3. So this is pretty much a review of last time, but it's always good for practice. So we're going to construct a dot plot of the following numbers. So first you're going to make a number line, and then you're just going to, enter in our data here. So I should have drew the dot plot a little closer, but that was my fault. I thought it was going to be larger. But so I first made my number line, which is the black number line here. And I knew, okay, my lowest number is 0, my highest number is 51. So I just wanted it all to fit on the page this time. And then I'm going to go through the data and put a dot where each data point belongs on the number line. And if there's, more than one specific number, then I'll start, layering on top of one another. So to construct the dot plot. And this gives us an idea of the frequency of the different, measurements in our data, or in our sample. Okay, so first we have here, I'm just gonna keep this and you can follow along. So our first number is 0, so I put a dot here. Then our next number is 1, then 2, then 12 and 12. So there were two 12s, so I put it directly on top of each other. Then 14, then 18, then 21 and 21. So there were two 21s, 23, 24, 25, 29, 29. So there's two 29s. And then there's three 30s. So I did three dots on top of each other. And then 33, 36, 44, 45, 47, and 51. And that is it for question 3. All right, then we have, okay, 2 more pages left. So ignore the lines right now, they'll become useful in part D, but right now pretend those lines are not there. So is this a frequency histogram or a relative frequency histogram? So this would be a frequency histogram. And you know, the y-axis is a big indicator of what type of histogram we're looking at. So here we're just looking at the frequency, not the relative frequency. All right, so how many measurement classes were used in the construction of this histogram? So we're going to count how many like buckets or bins there are. And a way to visualize is pretend that each range here, so like 0 to 5 is a bucket, 5 to 10 is a bucket, 10 to 15 is a bucket, and so on. And so if you were to go through with your list of data points, whenever you have, let's say, for example, a 2, I'll put that in the 0 to 5 bucket. And then whenever we have, let's say, a 8, I'll put it in this bucket. And so that's kind of, if you visualize kind of going through your data point by point, putting it in the bucket it belongs, you'll end up getting, like a histogram. That's just a way to visualize it. So how many measurement classes, or how I like visualizing it, how many buckets are there to construct this histogram? So there's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 because there's 8 bars. All right, what is the mode of the histogram? So our mode is going to be located in this measurement class from 10 to 15 because it has the highest frequency in this bucket. So that would be class 10 to 15. And then we're going to construct the relative frequency of class 5 to 10. So I did this by hand, but notice that this is also the nutrition study fiber part. So you also could do a lot of this on R and it could be, more exact, but this I did by hand to kind of give you an understanding of what's actually happening. And so my answers will be more of an approximation. But you could actually find the mode, the specific mode, using R. So instead of just giving a class, which that's all I can give, because given this histogram, that's all I can give from it. But if you were to download the data and, use the mode function in R, it will give you the specific, the specific number. All right, so sorry. So to continue, so to construct the relative frequency, so doing it by hand, just approximating, this is what I use the numbers for, just to help me, look at the frequencies. So, so the relative frequency of class 5 to 10. So if we look at 5 to 10, that's this bar right here in the bar graph. So I ballparked that it was around 92, because directly the middle would be 90, but it's a little higher than the middle, so I guessed that it would be around 92. So I have 92 in the numerator, and then I need to divide that by the total number of data points. So here, I approximated the frequency of each bar in the bar graph to get the total. So for this first bar, which is the yellow line, it looked like that was around 9 to me. And then here, the second bucket from 5 to 10, class 5 to 10, I said this looked like 92. And then I'll add that to how many are in this bucket, how many data points. And so I guess that this would be around 130, that's the red. And then class 15 to 20 would be the green, and that I guessed was 59. And then our purple line, which is a little off, so 20 to 25 are data points that fall within that range. So I guessed that it would be around 19. And then for our 25 to 30 range, that looked like a 3, that there's 3 of our data points in that bucket. And then for these two last buckets, I guess that there was 1 data point in each of these. So when I add all of these together, so 9 plus 92 plus all of that, I estimated that our total is about 157. And or actually, no, it's not 157. This is the simplified version. I didn't actually add all of these out, sorry. So yeah, so when you simplify this fraction, you get 46 over 157, and our decimal version of that number is 0.292994. So that is our relative frequency of our class 5 to 10. So around, if I were to round, so 0.3. So 30% of the time, if you were to grab, let's say pull these, all of our data points were in a hat, and let's say you were to juggle the hat and, pull from the hat 30% of the time, roughly, you would get a number that's, falls between 5 and 10 in that bucket. So, yeah. All right. So moving on to question 5. So we have a box plot. So is the data skewed or symmetric? So it would be skewed. If it were symmetric, then it would actually look symmetric. So at the median, you would be able to, it would be like a mirror reflection on each side of the median. But if you notice that, this box on the right-hand side is a little longer, our whisker on the right, because some people say box and whisker plot. So our whisker on the right is longer than the left. And then we also have these outliers on the right. So this is definitely skewed. And then our part B is, what is the interquartile range? So we would take the 3, we would take quartile 3 and subtract it from quartile 1. So here this looks like 6, and here this looks like 3. So 6 minus 3 is 3. All right, and then we want to identify any outliers in the data. So here, any dots that are not part of the whisker would be outliers. So if I was like really trying to be exact, okay, that's like 11.9. And then the second one would be 13.8. And then the third one would be like 15.8. Because they don't quite line up with this line. And that is the outliers from the box and whisker plot, or the box plot. All right, so this concludes recitation 3. And just to recap, we covered, computing the mean and standard deviation again. As review, we covered the empirical rule, and we also covered calculations using percentiles. All right, I will see you next week.